Fire. Each year, fire accounts for nearly 6,000 deaths and 25 to 30,000 injuries in the United States. What is even more disturbing is that these figures have not declined much over the last 10 years. The problem in Canada is comparable. In a recent survey of industrialized nations of the world, Canada had the second worst fire death rate per million population. The United States was right behind, ranked third. Property loss from fire is also a serious problem. In 1986, fire losses, as measured by direct property damage, cost the American public nearly $7 billion. When indirect costs, such as lost profits or wages, medical treatment, increased living expenses, and so forth are considered, it is estimated that the total annual cost of fire approaches a staggering $30 billion. This graph from the National Fire Protection Association shows losses per structure fire adjusted to 1977 dollars. It indicates that, like fire deaths, property losses have also remained relatively constant over the past several years. Nowhere does the fire problem hit harder than in the home. Residential fires in the U.S. currently account for 61% of property damage in structure fires and 81% of all civilian fire deaths. The problem is compounded each year by new construction entering the housing market, much of which is multifamily. 1987 multifamily construction starts alone exceeded 327,000, having an estimated value of $14 billion. Providing fire safety for this type of housing presents a special challenge to the design community, since the careless actions of one occupant can place an entire building at risk, as well as all of its other occupants. Findings of a study conducted at the University of Maryland have shown that the risk of fire damage increases as building fire resistance decreases for both sprinklered and non-sprinklered buildings. In addition, a study utilizing data obtained through the National Fire Incident Reporting System specifically concludes that fire in combustible buildings is over 4.5 times more likely to spread beyond the fire-rated compartment of origin than in non-combustible buildings. Yet the full benefits of non-combustible fire-resistive construction are frequently being overlooked at local, state, and national levels. In some communities today, municipalities are adopting building codes that allow trading off structural fire resistance as an economic incentive to installing sprinklers. This results in almost total reliance on the sprinkler system for fire safety. If the sprinkler system fails for any reason, the redundancy needed to provide fire protection is simply not there. Trading off one form of protection for another is an inappropriate approach to solving the fire problem, since by definition, a trade-off is intended to maintain the same level of risk. Although sprinklers have the potential to reduce fire losses, by no means do they offer the total solution. Because sprinklers are mechanical systems, they are susceptible to failure and have other shortcomings. Only if sprinklers are required without trade-offs can they be certain to reduce fire losses. These scenes were the result of careless use of matches while trying to light a barbecue grill on a balcony. As the match fell to the ground, it ignited the dry grass, causing the fire to spread to the combustible siding on the building. The sprinkler system, which was overwhelmed by the fire, was ineffective because it was not intended to control fires of exterior origin. Had the walls of this building been concrete or masonry, the likelihood of a fire causing such disastrous consequences would have been greatly reduced. Logically, if both the walls and roof were concrete and masonry construction, it is very likely that the fire would have been controlled before it entered the building. Unlike sprinklers, which provide active protection, fire-resistive construction provides passive protection. Its performance does not rely on human response or mechanical systems. Because it is the last line of defense and stays in place even when other systems fail, it should be the first and foremost design consideration for fire protection. Concrete and masonry's inherent fire resistance and durability make them an excellent choice of building materials. Let's take a closer look at how fire resistance can be built into a structure. Compartments can be constructed like this, where building elements contribute to the building's combustibility. It's easy to see that this structure, when completed, will have a very high fuel load. Conversely, compartments can be constructed like this. Concrete and masonry materials add no fuel to a fire, thereby significantly reducing the overall combustible loading of the building. They also give off no toxic fumes or smoke when exposed to fire because they simply do not burn. In most communities, building codes only require 1 hour rated walls and floors to separate one tenant from the next. If the building is of combustible construction, compartmentation walls will usually be constructed of wood studs and gypsum wallboard. But is this enough? What constitutes adequate compartmentation? Recent studies conducted by the National Bureau of Standards show that the mean fire load in dwellings is 13 pounds per square foot of floor area. Using this fire load and the Lund Institute's rational design method for determining structural fire resistance, a method recognized by the Swedish Building Code since 1967, real fire curves can be plotted for various compartment fires. The curve shown here represents the time-temperature relationship that can be expected during a fire in a typical apartment. When compared to the standard ASTM E119 curve, it is readily apparent that the Lund curve exceeds temperatures developed during standard testing procedures for a range well beyond 1 hour. From this, one can logically conclude that 1 hour compartmentation is not adequate to resist a burnout in a dwelling unit of a multifamily building. The Concrete and Masonry Industry Fire Safety Committee recommends that dwelling unit separations be 2 hour rated concrete or masonry construction. In further support of this concept, full-scale fire tests of 2 wall assemblies were conducted according to ASTM E119 testing procedures. The intent was to visually demonstrate the difference in performance between a 1 hour rated combustible wall that would meet code requirements for tenant separation walls and a 2 hour rated masonry wall. To perform the test, the masonry wall specimen, constructed of 8-inch hollow concrete blocks, is assembled in a concrete testing frame. After the mortar has cured to 28-day strength, the wall is placed in the test furnace and subjected to the standard fire exposure for a period of 2 hours. Upon completion of the 2-hour test period, the assembly is removed from the furnace and positioned for a hose stream test. The hose test is not meant to simulate water from a firefighter's hose striking a wall under actual fire conditions, but rather is used as a tool for evaluating the wall's durability and resistance to the effects of cooling, erosion, and thermal shock. Here, the specimen is rotated such that the water will be directed at the fire-exposed side of the wall. As the water, under 30 pounds per square inch pressure, is directed against the wall, the effect of impact is seen. Wetting of the entire surface using a sweeping motion then continues for 2.5 minutes, the time requirement prescribed by ASTM E119 for a 2-hour fire-rated wall. This is the end result. Since the specimen was tested as a non-load-bearing wall, a passing grade entails successfully meeting specified temperature conditions during the fire endurance portion of the test and not allowing any water to pass through the assembly during the hose stream test. Because both requirements were met, assemblies constructed to the specifications of this test specimen would be considered acceptable for a 2-hour rated non-load-bearing wall. Similar results would be expected for load-bearing walls. In the second test, a 1-hour wood frame wall was tested, consisting of back-to-back layers of 3/8 inch and 1/2 inch common gypsum wallboard nailed to both sides of 2x4 wood studs 16 inches on center. The same procedures used to test the masonry wall were repeated, with the only difference being the shortened application of fire exposure and the hose test. For this specimen, the required fire exposure period of 1 hour is to be followed by a 1-minute hose stream test. Here is a view of the wall assembly through a rear window of the furnace, less than 45 minutes into the fire test. At this point, large sections of drywall have already fallen off, and some of the exposed studs are burning. Upon completion of the 1-hour fire exposure period, the specimen is removed from the furnace. It should be pointed out that the hose stream tests performed on both the masonry and wood frame wall assemblies were in accordance with the optional methods specified in ASTM E119. This method, which is more restrictive than the conventional method, specifies that the hose stream test be performed after the specimen has been exposed to the standard fire for the full rating period. In the conventional method, construction of 2 duplicate specimens is required. The first specimen is used to establish the fire resistance rating by exposing it to the standard fire for the duration of the fire endurance classification period. The second specimen, however, which is subjected to the hose stream test, is exposed to the same standard fire conditions for only 1/2 of the fire resistance rating period before conducting the hose stream test. Combustible assemblies, like the one shown here, use the conventional test method for reasons which will soon become obvious. Constructing and testing duplicate concrete or masonry specimens is not necessary because of the material's superior durability. In this demonstration, the optional method of testing was selected for the wood frame wall, since the purpose of the test was to compare the performance of the wood frame wall with the masonry wall, and not to establish its fire resistance rating. As the wall is being turned in preparation for the hose stream test, note that the fire has burned through both layers of drywall and consumed many of the studs. After the test frame is placed on the supports, the water is brought up to 30 pounds per square inch pressure and directed at the wall. Upon impact, the stream immediately penetrates the assembly, thereby terminating the test. These tests clearly illustrate the superior durability of the 2-hour rated masonry wall. Even though it has been exposed to 125% more heat energy than the 1-hour rated wood frame wall, it is still capable of performing its function as a fire barrier. This difference in performance indicates the increased level of fire protection that can be realized by upgrading building codes to require 2-hour rated concrete or masonry walls for unit separations in multifamily buildings. Compartmentation is not complete, however, without giving equal attention to floor and ceiling assemblies. Occupants should be protected from the vertical spread of fire as well as its horizontal spread. If vertical containment is not accomplished and fire spreads to a combustible roof, many lives and the entire building are at stake. Concrete floor and roof assemblies provide the degree of vertical compartmentation that is needed. Precast hollow core concrete panels adapt themselves especially well to this application for most multifamily building configurations. In constructing low-rise multifamily housing, the Concrete and Masonry Industry Fire Safety Committee recommends that the following considerations for compartmentation be observed. 1. Walls between units, corridor walls, and exit stair walls should all be constructed of concrete or masonry. If combustible projections, such as balconies and mansards, are present, separation walls should extend outside exterior walls and penetrate the combustible projecting elements. If a combustible roof is used, exterior walls and firewalls or area separation walls should be parapeted through and above the roofline. 2. Use cast-in-place concrete or precast concrete panels for floor ceiling assemblies. In most cases, this will eliminate combustible balconies and the need to parapet walls through the roof. 3. Construct exterior walls of concrete or masonry. This protects the building from exterior fires and reduces the risk of vertical spread of fire from one unit to the next, even when combustible projections are present. 4. Provide adequate fire stopping in compliance with the building code for penetrations, such as plumbing and other pipes, heating and air conditioning ducts, and electrical conduits. Utilizing concrete and masonry construction will reduce or eliminate combustible concealed spaces and thereby decrease the opportunity for errors of omission in providing and inspecting fire stopping. And 5. Provide fire-rated doors as required by code for horizontal openings and enclose vertical openings with concrete or masonry to prevent the spread of fire from story to story. In summary, the 5 principles of compartmentation are: provide adequate fire stopping where penetrations are present. Use concrete or masonry construction for unit separation walls, exit stair walls, and corridors. Provide fire-rated assemblies for horizontal and vertical openings. Construct floor ceiling assemblies out of concrete. Construct exterior walls out of concrete or masonry. Concrete and masonry building systems, as shown here, offer the best method for compartmenting low-rise multifamily structures, as well as a number of other advantages. For instance, pre-cut holes can be designed into concrete panels to accommodate vertical penetrations, such as sprinkler risers. Sprinkler installations are less expensive because combustible concealed spaces are eliminated. In meeting insurance industry standards for classification as a fire-resistive structure, concrete and masonry buildings qualify for the lowest property insurance rates. Savings in premiums over the life of the building can be shown to offset the cost of a sprinkler system many times over. In fact, in a cost comparison with a similar wood frame structure, the concrete and masonry building is substantially less costly over the life of the building, considering costs of construction, insurance, sprinklers, and mortgage. From both an economic and fire safety standpoint, it is this advantage that should be used as the impetus for the installation of sprinkler and detection systems and not the practice of trading off structural fire resistance. Physical and mathematical evidence presented earlier demonstrates why 1-hour rated compartmentation in multifamily dwellings is not satisfactory. Upgrading to 2-hour concrete and masonry compartmentation in multifamily dwellings will improve this nation's current and future fire loss record. But we must start today. The lack of significant improvement in fire losses over the past several years suggests that the time to re-emphasize the importance of structural fire resistance has come. With fire costing the United States $30 billion annually and thousands of lost lives, we cannot afford further delay.